Let's talk about concavity now that we've seen the second derivative. So basically that's what the second derivative measures. It measures a curve's concavity. Remember, a derivative measures a rate of change. So the first derivative was the slope, or how the y value changes as the x value changes. Well, the second derivative is measuring how the first derivative changes. So how the slope changes. And as I say, we call that concavity. Now, if the second derivative is greater than 0, the curve will end up being concave up. Because what we're saying is the slope is getting greater and greater because it's positive rate of change. So let's have a look at a curve that's concave up. Our standard parabola, y equals x squared, is concave up. If we start at the left, we've got a slope, which would be fairly steep if we're out near infinity, but it would be a negative slope. And as we move more to the right, that slope, it's getting, well, it's still negative, but it's getting shallower and shallower until you hit the origin, then it's 0. And then when you start going up the other side, now it's going positive, starts shallow and gets steeper and steeper. So its concavity is positive. The rate of change of the derivative is positive. It's getting bigger and bigger. So concave down is the other way around then. So when that change in slope is getting smaller and smaller and smaller, and then ends up getting more negative. We call that concave down. So what happens in the middle? In the middle is a possible point of inflection. A possible point of inflection. So a point of inflection is where it changes concavity. We'll talk a bit more about that later, about why it's only a possible one. Okay, so now we're going to draw a sketch, but only using the second derivative this time. We'll get a rough sketch of what this one looks like. So first derivative, second derivative, 6x plus 10. So concavity, what I'm interested in is when is it concave up, when is it concave down? So I'll find when it's concave up. Again, I explain what I'm doing. All right, I know the curve is concave up when the second derivative is greater than 0. So I want to solve this simple little inequality, and I get x is greater than minus 5/3. So minus 5/3 is the key point, I guess. So at x equals minus 5/3, we know that is where it's going to change concavity. So I must end up with something like that, where it's concave down on the left-hand side of minus 5/3 and concave up on the right-hand side of minus 5/3. So once again, I haven't bothered to find the x-intercepts or the y-intercepts. Easy to find. That's just 2, of course. But you know, I haven't bothered to actually formally find that. It's just a rough sketch using only the second derivative. Okay. What this now does, it gives us a more efficient way of working out maximum turning points and minimum turning points. Because now if we combine our first derivative information with our second derivative information, right, so we know all the turning points are going to be stationary points. So we know the first derivative is equal to 0. So if you like, that's the condition. First thing that has to happen has to be a stationary point. So we find that first. Then we have a look at the curve's concavity. Now, if it's concave up, and it's stationary, even though it's wobbling, okay, it must be a minimum turning point. So I combine the two bits of information. If it's concave down and stationary, then it must be at the top. So it must be a maximum turning point. And that can save a bit of time, because now we don't have to draw up those table of values. However, don't discard that idea completely. Because if you've got something that's difficult to differentiate, so you differentiate it once, you go, oh my God, now I've got to differentiate again. Well, it's probably going to be easier to draw up the table of values and just use the first derivative either side than spending a lot of time trying to differentiate a difficult function. So it's still a good technique. All right, let's find them. For this, again, we're still pretty much stuck with polynomials at this stage. So first derivative, second derivative, so I work out all my tools that I'm going to use. Again, explain what you're doing as you go through it. First thing I'm doing, I want to locate these stationary points. I know they occur when the first derivative is equal to 0. So we'll solve that quadratic, and we end up with 1/3 or -1. Now, instead of drawing up the table of values, I just got to have a look at what the concavity is doing at those points. So at x equals -1, I end up with -4. The actual number is not that important. We're more interested in, is it negative or is it positive? 4, I guess, tells us the pace of the change. So all right, that one's less than 0. Get it right this time. Concave down. All right, we must have a maximum turning point at minus 1, 2. Let's have a look at the other one. Positive 4. It's a coincidence that both those numbers are 4. Right? But mind you, it's surprising how often that happens. And I guess that's because a lot of these shapes are sort of symmetric around the inflection point. So yeah, well, the Y value is nice, isn't it? 22 and 27. There's our minimum turning point. All right. Well, let's talk about those points in the middle. Inflection points. So, as I say, a point of inflection is where there is a change in concavity. Well, just like we did with the first derivative, draw ourselves up a table of values. Let's see what's happening either side of the possible inflection point to see whether it does indeed change concavity. So find the inflection points of this. Now, of course, we're going to get an inflection point. It's a polynomial, it's a cubic. It must have an inflection point. All cubics have inflection points. Okay, but let's pretend we don't know that. Okay, first derivative, 12x squared plus 12x. Second derivative, there it is, 24x plus 12. Possible points of inflection. There are curves where the second derivative is equal to 0, but it's not an inflection point. And I guess the easiest one to think of would be y equals x to the power of 4. Right? Because you differentiate x to the power of 4. First derivative, 4x cubed. Second derivative. Okay. Now, at the stationary point, 0, what's the second derivative? 0. But it's not an inflection point. We know x to the power of 4 is a turning point. Okay? So that's why we say possible point. It might not be, and that's why we need to test it. So let's have a look. Well, find it first. It's x equals negative half is our possibility. Plug it into a table of values, much like we did with the first derivative, but now we're checking the second derivative. So minus a half. Well, I've drawn a straight line for no concavity, but so a point on the left-hand side, a point on the right-hand side. Again, not going past any other stationary point or any other discontinuity. I'm going to use negative 1. Negative 12, we have a sad curve. Minus a half on the right-hand side, I'll choose 0. We have a happy curve. It is important that you write, your conclusion. There is a change in concavity. So you're explaining why is this possibility an inflection point? Well, it's an inflection point because I've found that yes, it does have a change in concavity. So therefore, minus a half 3 is a point of inflection. Horizontal point of inflection is a very special type of inflection. It's a point of inflection that is also a stationary point. Okay? The cubic being the classic one, y equals x cubed. So if it has a horizontal tangent, not all points of inflections have horizontal tangents when you draw them. Think of the tan curve. When the tan curve goes through the origin, that's a point of inflection. It changes concavity. But that goes through at 45 degrees. So it's a point of inflection, but it's not a horizontal point of inflection. Horizontal point of inflection, first derivative is 0. Second derivative is equal to 0. And there's a change in concavity. Third derivative is not equal to 0. What? Oh, here's a question. An alternative way of finding inflection books. You will not find this in textbooks for some reason. People, I don't know why they steer away from it. Just follow my logic. What is an inflection point? I just told you what it is. What is it? It's what in Gosh, if only we had a mathematical tool that measures the change in something. What measures the change in a function? So logically, the third derivative must measure the change in the second derivative. Okay? So, we would still find our possibilities. The second derivative is equal to 0. Now, this is the actual rule. If the first non-zero derivative, so the first time you substitute it into the derivative, and you get an answer that's not 0, if it's of odd order, third derivative, fifth derivative, seventh derivative, ninth derivative, I sincerely hope you don't get anything where you have to go up to the seventh derivative and the ninth derivative, highly unlikely, then it will be a point of inflection. If the first non-zero derivative is of even order, so fourth derivative, sixth derivative, eighth derivative and so on, then it won't be a point of inflection. You can't conclude it's going to be a turning point though. It might be, but you can't conclude that. Right? So, in our example, the third derivative turns out to be a constant 24. So now how would I complete my solution? Remember, I've gone and found the possible inflection points. I'd then go, well look, when x equals negative a half, the third derivative is 24. It's 24 everywhere. Well, 24 does not equal 0. But again, that key phrase we write down, what does this mean? Well, there must be a change in concavity because the third derivative has a value. So, you know, okay, the size of the change is 24. I don't really care about that. But it has a value other than 0. If it was equal to 0, we're saying, oh, well, there is no change in concavity. So therefore, it's an inflection point. Okay. All right. Exercise 4E. A jolly good fellow. Oh, there it is.